Good day, esteemed researchers and curious minds tuning in from around the globe. We're here to delve into the fascinating world of Galactica, a large language model for science. This groundbreaking research explores how language models, like Galactica, can revolutionize our interaction with scientific knowledge, moving beyond the traditional store and retrieve paradigm. Prepare to be intrigued as we discuss how these models absorb technical knowledge, bridge scientific modalities with natural language, and potentially take on tasks that are currently human specialisms. Let's embark on this scientific journey together. The traditional method of storing and retrieving scientific knowledge has been prevalent for over half a century. However, it heavily relies on human effort, leading to a significant bottleneck in knowledge throughput. Language models, on the other hand, have shown promising results in tasks such as citation prediction and knowledge-intensive question answering. Yet, these models face their own challenges. The availability of high-quality, step-by-step datasets is a current bottleneck for language models. This limitation hinders their ability to perform tasks in the same way humans do. Despite these challenges, the potential of language models to revolutionize the way we access and process scientific knowledge is undeniable. Diving into the key highlights of our research, we've discovered that language models can serve as powerful absorbers of technical knowledge. This includes complex elements like LaTeX equations and chemical reactions. We've utilized a unique approach known as the working memory token, which has enabled us to achieve impressive results on mathematical MMLU and math benchmarks. In addition, our research has also shed light on the potential of large language models, or LLMs, to serve as a bridge between scientific modalities and natural language. To facilitate this, we've trained a fast text classifier to identify web pages with scientific content within the Common Crawl dataset. This approach has opened up new avenues for extracting and utilizing scientific knowledge. Take a look at this illustration. It depicts a human using internal or external working memory to solve a task, such as calculating the average of a set of numbers. This is a powerful analogy for how language models absorb technical knowledge, mirroring human cognitive processes. Now, let's consider the traditional method of accessing scientific knowledge. It's based on a store and retrieve paradigm. This approach, while effective, heavily relies on human effort for reasoning, combining, and organizing information. As a result, we encounter a significant knowledge throughput bottleneck. This is the problem we're addressing. We're exploring how language models can disrupt this paradigm and create a new, more efficient interface for humanity to access knowledge. Our research proposes language models as potential disruptors of the traditional store and retrieve paradigm. These models can serve as a new interface for knowledge interaction, capable of absorbing technical knowledge like LaTeX equations and chemical reactions. Large language models, or LLMs, play a significant role in this transformation. They can act as a bridge between scientific modalities and natural language, potentially improving the efficiency and effectiveness of accessing scientific knowledge. Our methodology involves the use of a fast text classifier. This tool is trained to identify Common Crawl web pages with scientific content, introducing a novel method in the context of scientific knowledge access. This approach allows us to harness the vast amount of information available on the web and use it to enhance our understanding of scientific knowledge. Our research delves into the potential of language models as powerful absorbers of technical knowledge. We've found that these models can effectively handle complex tasks such as LaTeX equations and chemical reactions. We've also employed a working memory token approach, which has shown promising results on mathematical MMLU and math benchmarks. In addition, we've begun to explore the potential of large language models, or LLMs, as a bridge between scientific modalities and natural language. This could revolutionize the way we approach tasks like IUPAC naming and drug discovery. To delve into the technical aspects of our methodology, we trained a fast text classifier to identify web pages with scientific content within the Common Crawl dataset. However, due to the poor quality of extracted text, we opted not to process pages using LaTeX. Furthermore, we've been investigating the potential of instruction tuning. This approach allows us to fine-tune our models without the need for direct comparison through ablations. This could open up new avenues for improving the performance of our models in the future. Our research utilizes a diverse set of 600 domains to train a fast text classifier, and we've assembled a list of academic domains, processing PDFs from these using GROBID. In our experiment design, we've demonstrated that language models can outperform tuned sparse and dense retrieval pipelines for citation prediction. Furthermore, we've shown that these models can compose a curated knowledge base for knowledge-intensive question-answering tasks. In terms of technical results, our findings indicate that language models are strong absorbers of technical knowledge. They've shown impressive performance, outperforming existing methods on MMLU and math benchmarks. This suggests a promising future for language models in handling complex knowledge tasks. Our research has yielded some key results that underscore the potential of language models in scientific knowledge absorption and application. Firstly, we found that language models can effectively absorb technical knowledge, including LaTeX equations and chemical reactions. This ability scales smoothly with the size of the model, demonstrating a promising trend for larger, more complex models. Secondly, we've seen language models outperform existing methods on mathematical benchmarks such as MMLU and math. This suggests that these models can be powerful tools for tasks that require complex reasoning and problem solving. In the realm of citation prediction, language models have shown superior performance compared to traditional retrieval pipelines. This indicates their potential in navigating and understanding the vast landscape of scientific literature. We've also found that language models can compose a curated knowledge base to perform well in knowledge-intensive question-answering tasks. This ability to organize and apply knowledge in a step-by-step manner opens up new possibilities for automated reasoning. Lastly, we've demonstrated that it's possible to formulate drug discovery tasks like MoleculeNet in a natural language prompt, and it achieves strong results without direct fine-tuning. This suggests that language models could play a significant role in future scientific research and discovery. Our findings indicate that language models have the potential to revolutionize the traditional method of accessing scientific knowledge, which has been largely based on a store and retrieve paradigm. These models have shown impressive performance in absorbing and organizing technical knowledge, suggesting they could serve as a new tool for exploring the vast body of scientific literature. However, to truly mimic human-like task performance, these models require an architectural change that supports adaptive computation. This is an area we believe warrants further exploration. In addition, our research has shown promising results in the realm of drug discovery. We've found that tasks like MoleculeNet can be successfully formulated in a natural language prompt, demonstrating the potential of language models to act as a bridge between scientific modalities and natural language. This opens up exciting new avenues for the application of these models in various scientific fields. As we conclude, let's revisit the key contributions of our research. We've delved into the potential of language models to revolutionize the traditional methods of accessing scientific knowledge. Our findings show that these models can effectively absorb technical knowledge and excel in tasks that require intensive knowledge. We've also investigated how large language models, or LLMs, can serve as a bridge between scientific modalities and natural language. This opens up exciting new avenues for scientific exploration and understanding. In our methodology, we utilized a fast text classifier to sift through Common Crawl web pages and identify those with scientific content. We then processed PDFs from academic domains using GROBID, a tool that extracts and processes bibliographic information. The figure displayed here provides a distributional comparison of citations, further illustrating the impact and reach of our work. In essence, our research paves the way for a new era of scientific knowledge access and exploration, powered by advanced language models.